Good morning all of you. In this video we will discuss about power transformation, what power transformation is and when to apply power transformation, and at the end of this video we would do some coding part also. So without much delay, let's jump into our slides. As you can see here, power transformation is same as log transformation. It changes your skew distribution to Gaussian. Here Gaussian means normal distribution. Yes, and we all know what normal distribution is. Yes, where mean equals to mode equals to, or which is elongated to your both side equally. Yes, so such distribution is called normal distribution. And I have talked about different types of distribution: normal distribution, skewed distribution. Yes, in my previous video. If you haven't watched that video, I will put the link into my I button. Yes, you can just go there and watch that video. So power transformation changes your skew distribution to Gaussian distribution, and normally there are two techniques of applying the power transformation. One is Box-Cox, second one is Yeo-Johnson. Both works normally, or both changes your distribution to normal one, and Box-Cox and Yeo-Johnson is applied on right-skewed data. Yes, because it is same as that of log transformation. Yes, in log transformation also we apply it to the right skewed data, and to the left skewed data we apply square transformation or other type of transformation. Box-Cox transformation. So as we know that Box-Cox transformation is applied on right skewed data. As you can see in the figure also, this is right skewed data. Yes, and this is before applying the power transformation, and after applying the power transformation your distribution look like this. This is your normal distribution, and same applies for this figure also. This is your right skewed data, and after applying the power transformation, now your data will be Gaussian, or try to act as a Gaussian distribution. And mathematically the formula for Box-Cox transformation is yi power lambda minus 1 power divided by lambda. Here lambda means the power, and the exponent. Yes, which normally varies from -5 to 5. And what we do is we go on choosing the optimal value of lambda. Your value of lambda can be 1 also, it can be 2 also, it can be 3 also. Yes, so we go on finding the optimal value of lambda. And one thing you have to make sure that while you apply Box-Cox, all the data inside your feature are all positive, because in negative distribution your Box-Cox transformation does not work. And if you have the negative data also, then here is the one, Yeo-Johnson. Yes, it is the updated version of the Box-Cox, or specialized version of Box-Cox, where it can be applied on both negative data as well as positive data also. This is the formula for this, and look at this. This is slightly your right skewed data. Yes, and after applying Yeo-Johnson, now your distribution look like this, which is almost normal. Yes, so this is all about Yeo-Johnson and Box-Cox. Yes, now we would be moving towards our coding part. Okay, so we are currently in our Kaggle notebook. Yes, and if you don't know about the Kaggle, it is a platform where you can work with machine learning and data science project. Yes, there you can find a lot of data sets where you can go and explore it. Yeah, so as you can see here, we have these libraries. Yes, we require pandas, we require numpy, matplotlib and c1. Matplotlib and c1 is used for data visualization, and we have one scikit-learn power transformer also, because at the end of the day we do not do it manually, we use the library, and here we are using scikit-learn power transformer. I have taken one data set from the Kaggle. My data set looks like this. Yes, we have around 600 rows with 13 columns. Yeah, we do not apply power transformer to all these columns, but I have taken 2 columns. Yes, and store it into X. So these 2 columns we would be applying power transformer. We would apply both Box-Cox also and Yeo-Johnson also, and see the difference. Yeah, and first of all we should check the value of y. Why? Because we know that Box-Cox works only on positive value. Yes, and if you have any negative value in your feature, then you have to use Yeo-Johnson. So let's check that. For that we use describe function. As you can see here, on applicant income, the minimum value is 150, maximum value 81,000. In the same way, loan amount minimum value 9, maximum value 700, means no negative value in both features. Yeah, so let's let's plot the KDE plot. We know what is KDE plot. Yes, we had talked in our previous video also on function transformer. Yes, if you have not watched my video, then use the I button and go to that video and know what is KDE plot and what is normal distribution, skewed distribution. There you can get plenty of information. So KDE plot, what KDE plot does? KDE plot is also same as histogram. Yeah, it plots the density, the availability or the repeatedness of the number. So as you can see here, I have used 2 columns here, and as you can see here, both are right skewed data. Can you see it? Yeah, this is the co-applicant income and this is fully right skewed. Yes, and this is also fully right skewed, the loan amount. Yeah, now first of all we would apply Box-Cox and we would apply Yeo-Johnson. Yes, so first of all Box-Cox, from scikit-learn power transformer object. Yes, we are creating a new object, and under that we are using power transformer, and you have to mention the method. This is the most important part. Yes, which method you want to choose. This time we are choosing Box-Cox. Yeah, and if there is some negative value also, then you have to choose Yeo-Johnson, but here no negative value. Yeah, so you can choose either Box-Cox or Yeo-Johnson, but this time we are using Box-Cox. And transforming our X means 2 features. Now as you can see here, now we would again plot the KDE plot. This time we have used X new Box-Cox, which is the transferred version of Box-Cox, transferred version of data after applying the Box-Cox transformer. As you can see here, now look at the distribution of your data. Your KDE plot is clearly showing that this is your normal distribution, which is elongated almost same to both sides, and this is the perfect one, the lone amount. This is the perfect Gaussian distribution. Yeah, so it is clearly seen that after applying the Box-Cox transformation, your distribution, your skew distribution is now Gaussian, somewhat Gaussian. Yeah, not fully, but yeah, tend to look like Gaussian. Now let's apply Yeo-Johnson transformer. All the process is same, but one thing is different, that is method. This time we are using Yeo-Johnson. We again fit to our x. Yeah, and finally after applying Yeo-Johnson power transformer, we plot it using KDE plot. Now look at the distribution. Yeah, same. Why the distribution is same for both Box-Cox transformer and Yeo-Johnson transformer? Because the data set is same. Yes, you do not have the negative value also, so that is why your distribution after applying the Box-Cox and Yeo-Johnson looks similar. Yeah, so at the end of the day you can check both the transformer. You can check the Box-Cox also, you can check the Yeo-Johnson also, but if you have negative value, I again repeat that your Box-Cox would not work on that time. So this much for you guys. Yeah, if you like my content, please like, share and subscribe my video. Thank you.